The next talk will be given by Tomás Vörös, and it's about different topic, determining the mineralogical density of meteoroids. And you have 15 minutes.
Hi everyone, this is my first time here. So to introduce myself, my name is Tomás Vörös. I am the newest addition to the family of PhD students of Juraj Toth. And I will be talking about determining the mineralogical density of meteoroids using the meteor observations. We can define density of meteoroids in two ways. First, we have bulk density, that is the simply mass of the meteoroid divided by its volume, simple. Then we have mineralogical density, and that is the mass of the meteoroid divided by the volume only of the material. So this way we define the density of the substance itself, and therefore by definition the bulk density is always lower than mineralogical density. Why do we do this? With the knowledge of both densities we can infer something about the material composition, whether it was some icy, asteroidal, or dense refractory meteoroid, or even we can calculate the porosity, so we can say something about fragility, for example. How do we calculate the mineralogical density? It's based on the solution of heat equation during the preheating phase, so even before the meteor becomes visible in the sky. Without too much words, here's the solution. On the left-hand side, there are some parameters. These are only the material parameters of the meteoroid, so that is thermal conductivity of the material, mineralogical density, specific heat capacity, and also the temperature at which the material ablates, starts ablating. There is mineralogical density because we use heat equation and only the material conducts heat. Therefore, it would not make sense to use bulk density in the heat equation. And on the right-hand side, it is interesting that there are only quantities that can be observed by meteor observation. So that is the beginning height, entry speed, and the angle of its radiant. So how to use this equation? It was found out by Benyuk in 1968 that you can open the book with material parameters and you can list, for example, iron and plug in the parameters for iron, and now you know that iron with this mineralogical density has some value of this left-hand side of the equation. Then you find quartz, and this way you create a list of materials that have some mineralogical density and the corresponding left-hand side of this equation. Then you go outside and observe meteors. You observe beginning height, entry speed, zenith angle of radiant, and plug it into the right-hand side. And they are equal. You already have the list of left-hand sides, and from observation you have some new value of right-hand side. So you look at your list and you say that, wow, this meteoroid has mineralogical density somewhere between basalt and granite, let's say. Or you can interpolate between the basalt and granite to obtain more precise result. But this is an analytic solution of heat equation, and for that some assumptions were needed. One of such assumptions is that the meteoroid must be large enough. What we are looking at is the result of our numerical simulation. This is a small part of a spherical meteoroid. It is the cross-section, so here at the surface, its temperature when it begins ablating is 1800 kelvins, and deeper under surface it's much lower. This one is so big I could not fit it on the slide, but you see that the surface layer that gets heated before the ablation starts, it's much thinner than the meteoroid itself. So that is what I mean by very large meteoroid, that only this thin surface layer gets heated. But what if we encounter such meteoroid? the assumption doesn't hold and we cannot use the previous formula. So we've decided to solve it numerically. Our input data is already mentioned, beginning height, entry speed at zenith angle of radiant. For that we use AMOS all-sky cameras operated by our faculty. And then, as is obvious from the previous slide, we must know the size of the meteoroid or its radius if we assume spherical shape. For that we use the method with meteoroid erosion by Juraj et al., which allows us to determine the initial mass and bulk density, and therefore we calculate the size of the sphere. So firstly, we model the luminous phase, and then we go back in time to model the preheating phase. And all our simulations are run in this atmospheric model used to calculate density. We have already heard a little bit about rotations. We assume that the meteoroids do not rotate, which is a conclusion of work of Babajanova and Konovalova. But I would say that their conclusion should be worded like this. They do rotate, but it's negligible during the duration of meteor, so we can assume that the heat flux is coming only from the one direction all the time. And we also actually tried to distribute the heat flux uniformly on the sphere, but in that case we obtained mineralogical densities usually lower than bulk densities, so by definition wrong. So the assumption of very fast and random rotation does not bring physical results in our case. Next, we simulate the meteoroids as black bodies that radiate energy away because they are quite hot. So the heat flux is calculated as Stefan Boltzmann constant times the surface temperature to the power of 4 minus temperature of the Earth to the power of 4, because Earth is also roughly a black body that radiates towards the meteoroid, but that's a really small detail. What is not a small detail is the fact that the material parameters change with the temperature itself, which we can see as the example of iron thermal conductivity on the left-hand side, changes by a factor of 3 in our range of temperatures, and the same for another material parameter, thermal diffusivity. So now we know everything what we simulate, but the question is, when does the meteor become visible? Fortunately, recently there was an experiment in the plasma wind tunnel where they took some meteorite samples found on the Earth and burned them. Among many measurements, they also took temperatures of the surface, and it differed a little bit with composition, but when in our simulation, the meteoroid, as it is falling downwards, heating up, and once it reaches the required temperature to start ablation, we stop the simulation, and now we say that meteoroid is visible and its current height in the atmosphere is the beginning height that should be observed. So, to see it on an example, we simulated a sporadic bolide observed above Slovakia this January. We ran the simulation 6 times for 6 different materials. They are the black points on the plot. The leftmost is the iron, its density is the highest. And if this observed sporadic meteoroid was made of iron, it would have become visible at around 86, 87 kilometers. Each of these testing meteoroids is simulated for the same entry speed as was observed, same zenith angle of radiant, same atmospheric density that was calculated for the time and place. This way, we create dependence of mineralogical density on the beginning height, but only for this one specific meteoroid, because as I said, it requires the measurements of the specific meteoroid. Then we create a smoothing spline and draw a red circle on it. Red circle is drawn at 90.7 kilometers, that is the observed beginning height, and it corresponds to mineralogical density 3,626 kilograms per cubic meter. So on this example, I have shown how we determine mineralogical density of any meteoroid. We have also looked at some stream meteoroids. Here we see the bulk density determined by the method of Vörös I have already mentioned, mineralogical density and the calculated porosity, which simply said is the amount of empty space inside. And also in brackets are some results of other authors. Arids are a very new meteor shower. They were observed for the first time in 2021. And I'm not aware of any other work that studies their densities or other physical parameters, but they originate from Jupiter family comet. And these values in the table we have obtained are consistent with what we would expect from such material. We know Geminids are very interesting, and we have found that they apparently have too high mineralogical density, almost as if they were stony iron or something, which they certainly are not, and I will talk about it on the next slide. On the other hand, tau Herculids have very low bulk and mineralogical density and absurdly high porosity, which suggests that they are very crumbly and fragile. And indeed, our Czech colleagues also observed tau Herculids and found high fragility in tau Herculids. And also, interestingly, taurids have similar mineralogical density, but their bulk density is much higher. So, this is a plot of all the meteoroids we have studied. This is just observational facts. This is entry speed and beginning height on the vertical axis. And in accordance with the theory of heating, the faster the meteoroid enters the atmosphere, the higher it becomes visible. But look, here are purple taurids, and slightly faster orange Geminids, and even faster two brown dots, southern delta aquarids. It does not make sense. It's not in accordance with the theory we would expect, and we think it could be due to the fact that Geminids and southern delta aquarids have very low perihelion distances. That means they undergo thermal processing or volatile loss, and therefore the surface is altered. And at the very beginning, when we should observe the ablation of the surface, at the very beginning of the meteor, it is somehow different from other meteoroids that do not approach sun so closely. So therefore, we need more data on Geminids and southern delta aquarids, possibly even spectrums, to look into the abundance of volatiles. So that is all from me. If you don't know what should be your takeaway, I will tell you. I have shown that we can use the solution of heat equation to determine mineralogical density of meteoroids, but you should be very careful if you start interpreting your results, because some outliers are always there. Thank you.
Thank you very much. We have plenty of time. It works. It works? It does. We have plenty of time for questions again. Thank you. Yes, Jiri.
Yes, thank you. It was nice work. I have just two comments. I see the problem for determining the beginning height. First of all, it depends on the sensitivity of your camera. Second, it depends, as you suggested, maybe on the composition of the meteoroid, because we don't see only the heated surface of the meteoroid. We see in fact, mostly the ablated material. And if there is enough sodium, it first ablates earlier than other elements, so the beginning current is higher, and sodium is also very effective of radiating. So I think it's the problem with geminids and southern delta aquarids then have less sodium than some other meteoroids.
Regarding the beginning heights, the AMOS all sky cameras are quite sensitive. So I have read some article about Super Schmidt cameras. I think they had similar limiting magnitude to AMOS all sky cameras, and it should be okay for Super Schmidt cameras. So we assume it is also good for us.
I see we have a question online from Galina. Galina?
Yes,
Galina,
thank you. Yes, I missed key. And it was a comment. What I heard valuable for me in your talk was word fragile related to geminids. Many years ago, Tahtasiev, physicist from Kazan, and Belkovich, they thought that geminids are hard but very fragile. And I think that density close to 1 gram per centimeters cube is more close to reality than, say, 3 or 4. And recently, excuse me, my memory is not absolute, but probably Hanus with co-authors found the density of phaeton also between 1 and 2 gram per centimeters cube. So that is all. Thank you.
Thank you.
Yes, Peter.
Thank you very much. I want to come back to the question we had already about the beginning height. So did I understand correctly that you only used the AMOS camera data? So, okay, then we can assume that the parameters for the beginning height were altogether the same. So we have a consistency in there, but I think this is not comparable to video data of other systems, especially not for networks that have various cameras in their contributions. Thank you.
Okay, I think we have to move on to the last talk. So thank you again.